I'd like to tell you about work that we did on blue waters in the last year. We're studying brief episodes in stars, and we're working together with a team at the University of Victoria that's listed at the bottom, and we're at the University of Minnesota. So this is what is called a Kippenhahn diagram, and so I can't get the cursor, so I'll just tell you in English what you're looking at. The shaded areas that are these sort of vertical blobs are convection zones. Time is going from the left to the right. And you can see the little blobs appear at intervals of thousands of years. They are what are called helium shell flashes. When the star begins burning helium, when it has been burning hydrogen. And what we look for is an event where the convection zone that builds above the helium burning shell reaches up high enough to get to the unprocessed hydrogen. And so if that material can be incorporated into the convection zone, then it is brought down to a much higher temperature and burn very violently and release about 10 times as much energy as the helium burning itself. And so that produces a big reaction. And it also produces a variety of heavy element isotopes that you would otherwise not get. And that's the signature that is observational as those isotopes are spewed out later into the interstellar medium, and we can see them. We sort of wonder, well, where the hell did they come from? That shouldn't have happened, but this sort of a flash can be the explanation. And so this is where the vertical coordinate gives you radius rather than mass, and you can understand that when you turn on the helium burning suddenly, it's first heating up the layer right above it. Nothing much is going on, but it's putting in about 40 million solar luminosities, and eventually that just lifts the material up against the incredibly strong gravity, because this is burning essentially on the surface of what will become a white dwarf. And so gravity is incredibly large. It lifts it, and we tune in about in the middle of this picture where the material that is being raised up is incorporating some unprocessed hydrogen. And we will look, you can see this is measured in years, in time along the bottom, and the simulation we do lasts 2 days. And so during that time, the motion of the convection zone is quite small. Now, this is the actual star. That was a different star. This is the one we're really going to do with mass again. And the blue line is showing you the line below which there is no hydrogen. Okay, and so you can see it's going along. The shaded area is the convection zone above the helium burning shell. Aha. Thank you. And here you can see a different kind of shading, and that is because in this 1D stellar evolution calculation, we begin to burn hydrogen that the 1D code imagines is being pulled in. However, the process of pulling hydrogen in is not a one-dimensional process. One can model it, and this calculation tries to do that. But here, at a point where suddenly a lot of it gets pulled in, kind of all hell breaks loose, and my collaborator who does these things, Falk Herwig, says, well, just don't believe anything to the right of this sudden line right here. Okay, just don't believe it. Okay, we'll do that in 3D. And this is just showing that the length of time across that previous diagram is about 2 months, and in the 2 months, the top of the convection zone, which is this sharp part of the curve, has actually moved in radius. As I said, we're going to calculate for 2 days, but we wanted to calculate pretty much this time. And so what we did to cover 2 months in 2 days is that we increased the luminosity of the star. And this is a set of calculations we did that establish a nice scaling relationship, that if we double the luminosity, that's the energy dumped in from helium burning, then we double the rate at which the unprocessed hydrogen is being pulled down. And so we figured we had to go so far and we had so much computer time, and so we upped it by a factor of 22.5. And that might sound like a big factor to you, but it's not really so big because you take the cube root of it, and that tells you how much you have changed velocities in this situation. And so this is the velocity scaling, and it's the velocities that really create the situation that we are simulating. We've only upped them by a factor of 2.8, and they're still well below the speed of sound, where we can simulate them with our technique very well. This shows what the Mach numbers really are in this simulation. You can see the maxima are about 0.05, and if you ask what would 0.05 Mach number be outside in the air, it's 40 miles per hour wind. So it would not blow you over, but it's a pretty substantial wind. This is just to show that as we go through this calculation, there is nonlinear feedback between bringing the stuff in and burning it, which creates a release of energy and makes the wind larger. We're up to hurricanes, we're up to 100 miles an hour kind of wind, and it just keeps going. Well, this is something I'll tell you about later, and before you know it, we're up at Mach 3, okay? So at Mach 3, something really dramatic has happened. And my point is that there is an approach to this process that is slow, where we are bringing in this fuel. And then once the fuel is there, the process goes much more rapidly and violently. What I wanted to talk about was sort of the mechanics of how I did this, because I figured that more of you would be likely to get something useful out of my talking about that than telling you about this wonderful star. And so the first thing is that I want to characterize the way this thing works now. I think we've done a great job of scaling on blue waters now. That particular calculation, which made the movie you didn't see, ran with 64 cubed grid cells being updated on each node, running on 14,000 nodes, and with basically 26 time steps per second, and every 3 minutes a dump of about 50 gigabytes. And so that going on for a period of 4 days. Okay, 4 days over the month of August last year. I'm still hoping to kind of do that this August. Otherwise, I'm going to be not using my time, but I used it all in August last year. I'm not sure I'm going to be able to pull that off this year. But the point is that if I have a uniform grid, which I had in this calculation, I can do this scaling, I can make everything work. And what Falk Herwig and I have been talking about amongst ourselves over the last year are how many interesting problems can we do with this code without modification? And then we talk about what are the problems we really would like to do. And so this is a problem we would really like to do. And let me explain a little bit what it is. This is a 1D slice through a 1D stellar model. It's showing the entropy. And so these flat spots in the entropy are convection zones. And these things are showing energy release. So these are burning shells. This is a 25 solar mass star. It's burning oxygen here. It's burning carbon here. And then further out off the slide, it burns other things. And the idea of this is that in these stars, before they blow up, this is maybe 20 minutes before it blows up, it has these burning shells in layers, sort of like an onion going out, but in between them can be these very thin, stably stratified regions. And according to the theory of convective instability, these things don't do anything. They just sit there and keep this burning shell and that burning shell completely independent of each other. And we have done calculations like the one I tried to show you, where we compute ingestion from above a convection zone, and its after effects on how that convection zone evolves. And we can estimate how long it would take this convection zone to eat through this tiny little layer. And I told you it's got 20 minutes before it blows up. But it can get through it in 10 minutes or so. And so what happens when it eats through and starts ingesting burning carbon and all this stuff that's up here? My feeling is, well, whatever it does, it's going to be really great, and it's going to make a wonderful movie that I will learn how to show you, and that you will see and you will love. It's going to be fascinating. My colleagues in Canada have gone and done what they can in 1D, just sort of guessing what would happen, and they've decided that, gee, it's going to make all this scandium that you wouldn't get otherwise. And I've been told that scandium is used in high-performance bicycles, and therefore, my God, if you didn't get it, it'd be just a disaster. And so we would like to compute this. And the question is, how do we do that? If we put in a uniform grid, we know what it takes to do one of these problems, like the one down here with the oxygen-burning shell. It would take us those 4 days of the, all of that stuff. But then what about this? It has a much slower time scale. We would need to compute much longer. We would need to include this huge volume, and if we had a uniform grid, we would sort of go bankrupt. And so we are building a three grid level code, and I want to explain a little bit about this. We will have 3 levels in there, and just using that diagram, we can find out what volumes we would expect to have on each level, how much work it is, what would it be, and we would have 2 million grid breaks that we would have to spread out over the machine. And the way we would do them, it looks like we could fill a machine that had about 22,000 nodes. Which is, hey, blue waters, that's great. So it looks like with 3 grid levels, we could still fill the machine. The trouble is that, it'd be a bigger problem. And if we filled blue waters and blue waters didn't change, then we wouldn't be able to afford to do the calculation. And so what do? The idea is that we went through and figured out if our allocation didn't change and we had to do it the same way, we need a factor of 10 in performance to do this problem. And so here's some factors. We can get 2x by removing the base state and using 32-bit precision instead of 64, and watching Mao, the new graduate student who's sitting in the back, he's going to do it. And it's all going to be done by the end of the calendar year. It's just going to be fantastic. But that's only 2x. We needed 10. If somebody would buy some of these other things, we know what we get. We get 3.5x if they would refresh the hardware on the machine or something like that. And I think we learned in the last couple of days, that's not going to happen soon. So you can cancel that 3.5x. We could get a 2x by going from the CPU to a GPU. That would give us 4 altogether. And then there's this extra 1.7 that we learned as part of our investigation with this paid program and so on this year that we could get. And if you put the 2 and the 2 and the 1.7, well, it's not quite 10, but, well, maybe we could compute 5 days instead of 4. So we might be able to do it without their improving the machine, but it would certainly help if they improve the machine too. So I wanted to say what are the ways that we think we can get this speed. And the first is that we have a Cartesian grid, and we take our cells that look like this. Where's my, I don't know, I don't need a pointer. And we chop them up and we form these little briquettes. We treat the briquettes as a series of 4 grid planes, and we vectorize everything over these 16-word items that line up nicely. For the GPU, we need to do 2 of these simultaneous. The first thing is that by processing those briquettes and using the little 16 or 32-word SIMD arrays, we get a speed up that is already incorporated in our present code, and the speed up is about a factor of 6 over a simple code expression that we never used because it would be slow, but it was about a factor of 3 over the one we did have. And so that's a good thing. We have a situation where we are processing this in a pipelined fashion. So you can think of it as people sitting on a production line, sitting at workstations. This is non-copyrighted clip art. I'm sorry, it's the best I could find for workstations. And the idea is that these little arrows are vectors, and they're put in those little briquette record packages. And at the beginning of the production line, one of the briquette packages comes in, and the first guy unpacks it and starts doing some things with it, and it goes on down the line. And the idea is that at each next station, you can't begin what you're going to do until the previous station has done what it does twice. Okay, not just once, twice. So the way you start this whole pipeline up is you go and you do the first guy's task, and you pass it on, but the other guy can't do anything with that. Then you have to do the first guy's task a second time and pass it on. Now the second guy can also do his thing and pass it on, and so on. You eventually get everything going so that on each next iteration, you get a totally formed new briquette. The trouble with that is that it is a serial process. It's all vectorized and wonderful, and it's all done in on-chip memory, and it's just absolutely fabulous, but it's serial. What we discovered is through experimentation, let me find the right one. Through experimentation, we found that we could get more out of all of this if we would take the production line and ask everybody to do twice as much. Now, you could have had just 2 production lines. That's kind of the simultaneous multi-threading idea. But if you have 2 production lines, you've got all this infrastructure to support each one. If we have 1 and we ask everybody, instead of processing 2 grid planes, to do 4, for example, then we can get a doubling. And so I built a little code that just does part of our process to show that it really works. And this is kind of the result we got. If we look on a CPU, on these kind, we're getting about 1/4 of a teraflop out of a node. And if we could figure out, number one, we can give everybody more to do. We could increase their speed, but not very much here. But we discovered that, although the reading and writing of this data from the chip to the main memory was costing us nothing on the chips that are in Blue Waters now, on these fancier ones, we pay a heavy price. If we can figure out how to make the reading and writing cost nothing, and we're sure it must cost, it shouldn't cost anything, there's a factor of 2 to be had here. It turns out that that is true for the GPU as well, and Pei-Hung Lin, who has been working on that, has shown over here that with a K40 that he has available, that he can, by giving everybody one more thing to do, well, asymptotically, you get a straight factor of 2. And so I said 1.7x on the other slide because it's more like 1.7 for the CPU. But the point is, this is a substantial factor. And the way to do it is basically, it is a code transformation that is very similar to the unrolling of a loop, if you know what that is, except this is the unrolling of the entire 4,000 lines of Fortran. That is not one loop, it is many, 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 many loops, several, 20 subroutines and all of that. But it can nonetheless be effectively unrolled. And the reason it can be unrolled is because we pipelined it in the first place and made that wonderful thing. And so Pei-Hung, who has come and is in the back, he and I are talking these few days about just how he is going to do that. And he vetted the slide that is in here that I gave you, for the permanent record, that said that he agrees to do it. Okay? And so the idea is that we will just take this thing in appropriate form with a couple of directives, and we will send it to Pei-Hung, and it will just come back in like 1 second from his software translator, and it will be unrolled, and it will run twice as fast. And not just twice as fast on the GPU, but on the CPU, essentially on every device. And so this factor of 2, I showed you quite a few factors of 2 there, but this one I'm sort of proud of because we thought of it recently, and so I'm into it, but also because it was, for me at least, totally unexpected. And it seems to be, I thought, why couldn't it find something else to do? I give it this thing, why couldn't it do something else as well? I gave it thousands of just wonderful things to do, all in a line. And my theory is that it couldn't figure out how to do that because it only looks in a little window, and the next thing it could have done was, well, it was way down there and it just couldn't see it. And so this is a code transformation that will bring it into a position where it is visible and make it possible, basically, to do that. And so that's the conclusion from these tests, that doing this transformation really will be a benefit on all these different devices, and we will automate it, and then we'll have our factor of 10. And I've run out of time, so I will stop, but we also went through a process of discussing with the load balancing people at Illinois strategies for load balancing. And for the 3-level grid that I intend to use, there is a particularly simple strategy that we can take that we're at least going to try. And we think that we would be able to do the load balancing well enough so that it would not slow us down at all. We don't want to be giving up anything in all of these. By going to AMR, we would like to run as fast on each grid cell update as we have been with the uniform grid. In the process of going through the load balancing analysis and how we do that with the different time steps on the different levels, it turns out that there are overheads that I view as overheads of AMR that are of the around, we can identify ones that are around 25%, and we just pay it because we're doing AMR and we're winning because we have those core cells. So that's kind of anyone who's interested in those arguments or feels that they're totally wrong and they have to convince me, come see me after.